Hello everyone, this is Professor Gant and I'm here recording this Quiz 5 version E review, and I wanted to do this just in case we're in a situation where I'm either not able to be in class and we still have to um, go over this material. If we're not able to cover all the material in class, or if we have covered it and you just need to be able to look over everything again, and kind of fill in some holes on some concepts that you missed. So I'm going to go through each problem. We have 24 problems here on the review. Please know that whatever quiz you have, you won't necessarily be doing all 24 of these problems, but any one of these 24 could show up on your particular quiz. So it's important that you learn the concepts behind all of them so that no matter which type of problem you get, you know how to do it. All right, so let's start with question number 1. So for question number 1, we have two rational expressions, and we want to add these rational expressions together. And if you notice here, our denominators are different, okay? And we know that whenever we add or subtract fractions, we have to have like denominators, meaning that the denominator has to be the same. So for these two rational expressions, and what I mean by a rational expression is just an expression where your numerator is a polynomial, your denominator is a polynomial. So x plus 1 and x squared plus 2x minus 8 are polynomials. So we have a polynomial divided by 1 that divided by another polynomial function that's considered a rational function. So that's why I keep calling it that, okay? So what we need to do here is basically find out what our LCD is, which is least common denominator amongst these two denominators. Once we do that, then we can make equivalent fractions to make the fractions have the same denominator, and then from that we can just add like we normally would with fractions. So first thing that we want to do is just figure out what the denominators are going to factor out to be. So I'm just going to write it like this, and we know that for our first denominator it should factor out to something, second denominator should factor out to something else. Now for x squared plus 2x minus 8, since we do not have, we have understood 1 there, we know that this will start off being x here and x here whenever we use trial and error method. We know that since we have plus and minus, that means one of these will be plus, one of these will be minus here. And in the case of, since we have an understood 1 there, we ask ourselves, what two numbers multiply to be negative 8 but add to be a positive 2? And of course, what comes to mind is going to be 4 times 2, and particularly a positive 4 times a negative 2. And we know that because 4 times 2, or we'll say 4 times a negative 2 gives us a negative 8. But we know if we take 4 and add it to a negative 2, which is another way of saying 4 minus 2, we get a positive 2. So here we just put a 4 there, put a 2 there, and of course if we check the inner and the outer parts here, we'll get 4x minus 2x, which is equal to 2x, which is exactly what we need here. Okay. Now, following a similar sort of thinking here, we know that we have plus and plus. So we got plus and plus here. X squared factors out to x times x. And for 4, we know that 4 times 1 is 4, but 4 plus 1 is 5. So we have 1 and 4 that goes there. So as far as that is concerned, we have everything factored out. And so now what you see here is that x plus 4 is common with both rational expressions. But we need to find out what the LCD is. So I'm going to erase what I have here. All right, so we have all that erased. And so now again, what we see is we have x plus 4 is common in the denominator here. But we see that here we also have an x minus 2 and an x plus 1. So if we wanted to find what the common denominator is going to be, the LCD for these two fractions will just be x plus 4 times x minus 2 times x plus 1, okay? Because in order to make this work, this one has the x plus 4, the x minus 2, but it doesn't have an x plus 1. And this one has the x plus 4 and the x plus 1, but it doesn't have the x minus 2. So here when we rewrite this, we're going to rewrite it as x plus 1, and we're going to multiply the numerator by what this denominator is missing, which is the x plus 1. And all that over x plus 4, x minus 2, and x plus 1. So note here that we're essentially multiplying the numerator and denominator by x plus 1, and that's like multiplying our current rational function here by 1. We're just doing it in an equivalent way. So we continue on. Here we know that this one's missing the x minus 2, so we multiply the numerator and denominator by x minus 2. And I'm going to rewrite that the exact way that you see it so that you can kind of follow along. So we have x plus 1 here, then x plus 4, and then x minus 2. And that 4 didn't turn out so good. And that still didn't turn out good. All right, let's try this again. That looks a little better. All right. So now from this point, we know that the denominator is going to be the same because, of course, when we add two fractions, the denominator is going to be the same. So it'll be just x plus 4 times x minus 2 times x plus 1. In the numerator, we're going to multiply these two binomials together, and we'll do the FOIL method for that. And when we multiply these two together here, what we'll get is x squared plus 2x plus 1. And then when we multiply these two together, what we'll get is plus 2x squared, and then that's a minus 4x plus 7x, which will be a net positive 3x. And then 7 times a negative 2 is negative 14. Okay? So I'm purposely skipping the steps for multiplying two binomials together because at this point we should be comfortable with multiplying two binomials using the FOIL method. All right, so now we just need to simplify and finish. So here we have common terms of x squared and 2x squared, which gives us 3x squared. We have 2x plus 3x, which gives us 5x. And we have 1 minus 14, which is a negative 13. We'll take all of that and just divide that by what our LCD is. And this is your final answer. Please note there is no need for you to multiply the denominator together. Okay, there's not anything that you can gain out of doing that. And if you try to factor out the numerator, you would see that you're probably not going to find anything that it will factor out to. Okay, so that's why this will be the final answer. Now, one thing that you want to do is you do want to check to see will the numerator factor out in such a way to where it'll reduce with something in the denominator, but I can tell you in this instance it doesn't. So, and the main purpose of this problem is to just try to get you to figure out what is your least common denominator, and then from there form the equivalent fractions or equivalent rational expressions, and then just add. So that's all you need to do for question number 1. So let's move on to question number 2. All right, so for question number 2, it asks you to simplify what this expression is you see here And notice here that it says that all of your variables represent any real number. And what that means is it can be any number, whether it's positive, negative, or zero. Okay. Now, there is a few ways that we can interpret this problem and do it. I want to start off by just telling you what the answer is and then show you the different ways in which it actually becomes that. Okay. And want to let you know what you can do as a shortcut to just say, hey, I know that the answer is this. Versus in other situations, you won't be able to make that assumption. Okay. All right. So here, the answer to this question is just absolute value of x. Okay. Now, the reason that it's absolute value of x is because of the following. Note that in general, anytime we deal with a radical expression, what that radical expression actually is, it is an alternative way of being able to deal with variable raised to a fractional exponent. Okay. So, and in knowing that, I could also rewrite this and make this look this way. Using my exponential rules, I could rewrite this as x raised to the 1 over n times m. And I can also make it look this way. Okay. Now, what is my point in saying all that? Well, if I take the fourth root of x raised to the 4 and I rewrite this, this could be looked at as x raised to the 4 divided by 4. And we know that 4 divided by 4 is 1. And this is just equal to x. Okay. Now, the problem with this answer is that we have a fourth root. Okay. And one of the things that we know about even nth roots is that an even nth root can never be negative. So in other words, whenever we say something like, what is square root of 16? We always answer that with a positive 4. We never say that the square root of 16 is plus or minus 4. Okay. Notice that we don't answer it with a negative. Part of the reason for that is what the graph of what, in this case, x squared looks like. And what x squared looks like is a function that looks like this. Now, you don't need to know all this as far as what the graph looks like, but I do want you to recognize that this graph is strictly above the x-axis. So let's say if I wanted to say that here, if x is 16, then that's going to map up to a corresponding y value of 4. Okay. And my point is this: I have nowhere on this graph that says that, hey, the square root of 16, in other words, if I let x equal 16, it maps to a value down here where I have a corresponding value of negative 4. You don't see this point on that graph. Okay. And so because of that, that's the reason why we need to consider putting absolute value bars here. Okay. Now, to sort of give it to you another way, let's say I wanted to, and I'm just going to use a square root example again here. Let's say, and I'll just erase this for a moment. Let's say I wanted to do just square root of x, and I let x equal negative 16. Okay. Well, sorry, let me do this another way because I think this will be better. Let me erase that. So I'm just going to start with this, because square root of x squared is kind of like saying root 2 of x squared, or the nth root of x squared, kind of like what we see here. But we know that whenever we don't see the number here, the index, that's an understood 2. So my point is this: if I took this and let's say I let x equal negative 4, okay? So if I plug in negative 4 here, then I know that square root of negative 4 squared, I know that negative 4 squared is a positive 16. And I know that square root of 16 is just going to be 4. Okay. Now, if I change this and let this be positive 4 squared is also positive 16. And square root of 16 is also 4. And so what you notice here is regardless of whether your number is positive or negative, it could come out to be positive 4 here. But the thing is I have to make sure that the value of x that I'm considering, I can give it in all type situations. Okay. So if I was to not have the absolute value bars here, then literally what I would be saying when I say what is square root of x squared and I let x be negative 4, I'm saying that my answer to this, if I said, let me erase that. If I said, hey, let me do it like this, and I was not considering the fact that the values of x can be positive, negative, or whatever, literally I would say this. But again, the problem with that is I know that the even nth root of any number here cannot be negative because of what this graph says. Okay. And so because of that, I know that I cannot answer this with a negative 4. Okay. Another way to think about it is here, this is technically where x is negative 4. Okay. And if I was trying to take the square root of a negative number, of course, I know that that would be undefined. So here, in a sense, when I'm saying, hey, if I plug in x is equal to negative 4 and do that negative 4 squared and then take the square root of it, I would have this point on the graph. Notice that this part of the graph is not drawn. I don't have a part of the graph that's drawn like this to go with it. Okay, so that's why I can't answer it that way. Okay, so in all, to make this real simple, anytime that we assume that the variables are all real, any real number, and we have an even nth root here, we want to make sure that if this just simplifies to just x, if we did it this way, that we actually understand that it's absolute value of x, because we have to take into account of the positive and the negative values of x that it could be. But the only result for an even nth root will be a positive number. Okay. So I'm going to erase this again, work it out another way, and then we'll talk a few more things about number 2 before we move on. So in general here, we know that anytime we take the even nth root of something raised to that same index, we know that we're going to get absolute value of x. Okay. Now, another way I wanted to work this is, let's say we have 4th root of x raised to the 4, and per this interpretation, we could work it this way. Okay. Now, my point in saying this again is that we know that regardless of whether we plug in a value of x that's positive, negative, or 0, we know that the result of x to the 4th will always be a non-negative number, meaning that it's either positive or 0. Okay. And then, of course, if we take the 4th root of that, what we're essentially saying is we're taking the 4th root of some number that is either positive or 0, which, of course, we know that we always have to end up with a positive number or 0 as a result. Okay. So just mentioning that to give you another perspective on telling you why this answer would always have to be something that's non-negative. And the absolute value of x is a very concise way of saying, hey, no matter what x is, it has to be non-negative as a result. Okay, so just going to erase this, and then of course this will kind of be the same thing. We will just conclude that this just ends up being absolute value of x for an answer here. Okay. Now, to contrast what I'm saying with something different, let's say if you had cube root of x cubed. In this case, whenever you work this out, this will indeed just be x. And it doesn't matter whether x is positive or negative in this case, okay? And part of the reason for that is because when we take the cube root of a negative number, the answer is negative. For instance, when we say cube root of -8, we know that that is -2 because cube root of -8 actually means what number do I multiply times itself 3 times to get -8? Well, -2 is it. And if you multiply any negative number times itself an odd number of times, you're going to get a negative number as a result, okay? So again, we could also go with cube root of, let's say, -27. That would also be -3, because -3 times -3 times -3 would be a -27. And so my point here is that anytime you have an odd nth root, so let's say n is odd and it looks like this, then the result is just going to be x. And that's only in the case where n is odd. Okay? When n is even, you need to answer with absolute value of x. And that is the point of this problem, to make sure that you understand and respect that. Okay? Now, last thing I want to say here, I'm going to erase everything again, and then we'll move on, because what I'm about to say will actually help you in future problems. Now, for this problem, let's suppose that this says that assume that all variables represent any, and I'll erase this and say any positive real number, or it said any non-negative real number. In that case, you would work this just like how we did the one with the odd nth root. Kind of look at it this way and say, hey, the answer to that is x. Okay. Now, the reason why we can just say x here and not absolute value of x is because if x is, let's say, non-negative, then we're considering x to be greater than or equal to 0. So the smallest number we're considering is 0. And we know that the fourth root of 0 is just going to be 0. The fourth root of 1 is just going to be 1. And of course, the fourth root of any positive number that you put under there is going to end up being positive. So we don't have to worry about the situation where we have an even nth root of some number and it may turn out to be negative. We don't have that issue here. Okay. So whenever we have a situation where the directions say assume that all the variables are positive real numbers or non-negative real numbers, then we do not have to put the absolute value signs there. Okay. Just want to make sure that that's clear. And I know that for question number 2, we spent a lot of time on it, but it's going to help us out later on. Okay. All right, let's move on to problem number 3. All right, so for problem number 3, this was very similar to problem number 1. What's different about it is now we're doing subtraction instead of addition here. Okay. And yeah, I'm showing number 4. Don't want to show that yet. So just like how we did in number 1, we're going to figure out what the denominator factors to and then form an equivalent fraction from that. So x squared minus 16, we know that's the difference of 2 squares. That will factor out the x minus 4 times x plus 4. For the second denominator, that will factor out the x plus 1 times x plus 4. Okay. And so if you notice here again, what is the same is the x plus 4s. So our LCD here is just going to be x plus 4 times x minus 4 times x plus 1. Okay. So what that means here is that our first term is missing an x plus 1. Our second term is missing an x minus 4. So whenever we rewrite this, this would be x times x plus 1 in the numerator over x minus 4 times x plus 4 times x plus 1. And we'll fix that right quick. And that's minus 3 times, here we have x minus 4 over x plus 1, x minus 4, x plus 4. Okay? And of course, even though the order of the factors of the denominator are different in between the first and the second term, these two denominators are in fact the same. Because we got the x plus 4, x plus 4, x minus 4, x minus 4, x plus 1, x plus 1. Okay? Now, here's where this problem starts to be different than the problem in number 1. Of course, the denominator, let me erase that. Of course, the denominator is the same here. X plus 4, x minus 4, x plus 4, x plus 1. Okay. Now, of course, for the first term, we'll multiply the x's to both terms, and that'll be x squared plus x. For the second term, remember that this is minus all of this. Okay, it's minus all of it. So one thing that I do to make this easier for myself is I make this plus a negative, and I multiply the negative 3 by both of these terms here. So that will give me a minus 3x plus 12. Okay, and it's important for you to remember that when you have subtraction here, that understood negative 1 is being multiplied by everything in the numerator. Okay, and if you just make the subtraction sign plus and a negative on the number that's in front of this x minus 4, and then just multiply that negative 3 times both numbers in the parentheses, that makes it easier to deal with. Okay. All right. So from here, all we need to do is just simplify everything. So we only have one term that has x squared in it, so that's by itself. X minus 3x is a negative 2x, and of course 12 is by itself. And we'll put all that under x minus 4 times x plus 4 times x plus 1. And again, there's no need for you to multiply out the denominator here. And if you tried to factor out the numerator, you would see that you wouldn't have anything that would work to be able to reduce with any factor that's in the denominator here. So you just want to leave it like how you see it. Okay, so this is your final answer. All right, let's move on to number 4. Okay, so for question number 4, what we have is two rational expressions that we are trying to multiply together. Okay, and since we're trying to multiply them together, this is going to be a little different. We're not going to treat this like how we would do with the addition or subtraction. Okay, we'll do this a little bit differently because of the fact that we are multiplying. So all that we want to do is factor out the numerator and denominator of each rational expression, try to see what we can reduce to 1, and then multiply what's left. All right, so first thing, let's look at our first rational expression here. So we know that x cubed plus 1 is the sum of 2 cubes. And in general, whenever we have the sum of 2 cubes, we know that this is just going to be a plus b times a squared minus ab plus b squared. Okay? So if I did this where a is equal to x and b is equal to 1, then this would be x plus 1 times x squared minus 1x, or just x, and then that would be plus 1 squared, which is 1. In the denominator, note that here we have a common factor of x, They can be factored out of each term. And so that leaves us with x squared minus x plus 1. And that is what that first term factors out to be. For the second term, of course, 9x is just 9 times x. And negative 63x minus 63 has a common factor of negative 63. So when I factor out a negative 63, I just have an x plus 1 left over. Okay. So now that that's done, I notice here that the x squared minus x plus 1, all that will reduce to 1. I also notice that the x here and the x here will reduce to 1. The x plus 1 here and the x plus 1 there reduces to 1. And all I have left is basically a 9 divided by negative 63. And if you remember, 63 is just 9 times 7. Okay? Or to make this a little bit more simple for us, I'll switch this around and I'll say it's going to be a negative 7 times 9. Doesn't matter which factor you put the negative in. And so here, these 9s reduce to 1, and all I have now is 1 divided by negative 7, which is just a negative 1/7 for your final answer. All right, let's move on to number 5. So for number 5, this is much like how we did number 4. The difference is now that we're dividing instead of multiplying. So whenever we divide, remember, and I'll just make up a simple example here. Let's say if we did 2/3 divided by 3/7. Then if we were to divide these fractions, remember the keep, change, flip, meaning keep first fraction the same, change the operation of multiplication, and then flip the bottom fraction. Okay. And so in this case, we would do this, and then of course try to reduce what we can and multiply across. In this situation, nothing in the numerator will reduce with anything in the denominator, so literally you would multiply across. Okay. Now, just to kind of show you what happens whenever we do have reducing happen, I'm going to switch these two numbers here. So I'm going to put the 7 up here and the 3 down here. Okay. So in that case, remember we got keep, change, and then flip. So the 7/3 will now change to 3/7. And in this case, we see that these 3's here would reduce to 1, and 2 times 1 is 2, 1 times 7 is 7, and your answer will be 2/7 in that case. And that's kind of what's going on in question number 5 here. So just like how we did in question number 4, we want to factor out as much as we can the numerator and denominator for each term, but we want to do that after we apply the keep, change, flip that we know that we need to do. And part of the reason why I'm saying that you want to do the keep, change, flip first is because when we start factoring out the numerator and denominator of these rational expressions, that's going to involve a lot of work compared to doing the keep, change, flip. And so if you get caught up in doing all of the trying to factor out everything first and then reduce, you may forget to do the keep, change, flip. Okay. So we want to make sure that we do what's most important first, which is the keep, change, flip. And then after that, all the factoring we can do later. Okay. All right. So again, the first thing that we want to do is make sure that we apply the keep, change, flip correctly. So we will keep the first expression the same, change the operation to multiplication, and then flip the second rational expression, the second fraction. Okay. Now from here, we will go ahead and factor out the numerator and denominator of each term. So for the first term, we know that this will factor out to be x minus 8 times x minus 8. In the denominator, both of these terms have a common factor of 10. So when we factor out the 10, we'll have x minus 8 left in the parentheses. We know that 70 is just 10 times 7. And here, 7 and 56 both have a common factor of 7. And when we factor that out, it ends up being x minus 8 on the inside, because 7 times x is 7x. 7 times a negative 8 is a negative 56. And so now from here, we reduce what we can, okay? So we can start off by saying, hey, we have x minus 8, and x minus 8 reduces to 1. Another x minus 8, and the x minus 8 reduces to 1. We have 10, 10 reduced to 1, and we got 7 and 7 reduced to 1. So once we're done, we got 1 times 1 times 1 times 1, which is 1, or 1 times 1 times 1 times 1, which is also 1. So our final result just ends up being 1. Please note, for this particular question, you will only get full credit for it if all of your work is shown. Okay, you can't just simplify this and say, all right, well, I'm going to look at this, the answer is just 1. Okay, you can't get full credit for that. At most, you may get 2 points for that. So make sure that you do all your supporting work to show how you came to 1. Okay. All right, so for question number 6, I'll go ahead and show number 7 here as well. Question number 6, we want to figure out what this radical expression will be in its most simplified form. We want to assume that all variables are positive real numbers, if you have any, and we want exact answers, not decimal approximations. Okay. Now, in the question number 6, this one's pretty easy. Okay. Literally, you could probably plug this in your calculator and do it. But one thing that we know is that 15 times 15 ends up being 225. Okay. So what that means is that here, square root of 225, meaning what is the number that you would multiply times itself twice to get 225, would be just 15. And since this negative is on the outside, we just write the negative on the outside. And then from there, the answer to this would be just 15. Okay. And so that's all there is to that question. Okay. Now, the purpose of this question, whenever we say assume that all variables represent positive real numbers and give exact answers, not decimal numbers. Let's say, if I gave you something like this, what is square root of 80? Okay. Now, one thing that we know is that square root of, so not square root of, but 80, we know that it's 8 times 10, but we also know that it's 16 times 5. So I could rewrite this as square root of 16 times square root of 5. And here, I know that square root of 16 simplifies to 4. But square root of 5 does not simplify to anything exact. Okay, square root of 5 is an irrational number. And so if I tried to give the decimal approximation for it, it would not be enough. Okay, because the fact that square root of 5 cannot be represented as a fraction, so therefore it does not have a terminating or repeating decimal number that it can be represented as. So the most simple, most exact way you can express square root of 5 is just as square root of 5. So if you get a question that is something like this one, and you notice that, hey, I got some factor in there where I can't take the square root of it real easy, this is how you give that answer. Do not try to give the decimal approximation for 4 times square root of 5. I will not accept that at all. Okay. All right, so let's move on to question number 7. So for question number 7, this problem is asking us to, again, simplify this radical expression, assume that all the variables are positive real numbers, and give an exact answer. no decimal approximations. Now, for this one, since we just have y raised to the 11 inside of the radical, we don't have to worry about decimal approximations for anything. The only time we have to worry about that is when we actually know what the number under the radical is. And since we don't know what y is, we don't know what the number under the radical is. But that actually makes the problem easier by not knowing what the number y is. Okay, we do know that whatever y is, it has to be greater than 0. Okay, so anytime we consider an even nth root, we know that the even nth root of, let's instance, if I'm saying square root of y squared, I know in this case I can just answer with y because all of my variables represent positive real numbers. Okay, now if it was not the case and I was trying to do what is square root of y, and if it was not the case that y was just greater than 0, then I would have to answer this with absolute value of y. But we don't have that situation here. Okay, so you just want to make sure that we make note of that. So here we're able to answer any even nth root in terms of just y. All right, so one of the things that we know here is that y raised to the 11 means that we have 11 y's that are being multiplied times itself under the radical. Okay. Now, we know that anytime we have square root here, that is an understood 2 in the index. Okay, so in other words, the index is 2. And so one way to think about this is, hey, we need to figure out how many groups of 2 do we have in 11. And of course, we know that we have 5 groups of 2. Okay, so one way that we could write this, and I'm just going to write it this way, y squared 1, y squared 2, y squared 3, y squared 4, y squared 5. And then we just got another y left over. And here, for every 2 y's we have together under the radical, according to the square root here, we can take 1 out the house. So here we got 1 out the house for every 2 that's in. So that's 1, 2, 3, 4, 5. And then, of course, this last y here is stuck in the house because it doesn't have anything to pair up with. Okay. And of course, y multiplied times itself 5 times is just y raised to the 5 times square root of y. So that is one way we can get this answer. Okay. Now, another way we can get this same answer is if we look at this way. Okay. Y raised to the 11. We know that we could look at this as y raised to the 11 divided by 2, and that's per changing the radical form to fractional exponent form. So now if we look at this, we know that 11 divided by 2 is the same as 10 divided by 2 plus 1 divided by 2. And using our exponential rules, we know that we could rewrite anything that's raised to the sum of 2 exponents as just those same 2 things, in this case a, raised to those respective exponents. So a raised to the m times a raised to the n. So we could look at it this way. And 10 divided by 2 is just 5. And y raised to the 1/2 is just another way of saying square root of y. And we know that because, of course, y raised to the 1/2 would be the same as saying root 2 of y raised to the 1. We know that anything raised to the 1 is just itself. And we know that whenever we don't have a number written here, it's understood to be this 2. So that is another way to get the same answer. Okay. Now, one other way that you can think about doing this, and this is mostly mental, and this is sort of combining the 2 ways I've done here, is, let's get this looking right. So we know that anytime we do square root, or asking what will we have to multiply times itself twice to get this y raised to 11 in this case. And of course, we have an understood 2 here. And so again, like how we asked up here, how many groups of 2 do we have in 11? We have 5. And so since the only factor or only variable that we have here is 5, we know that since we have 5 groups of 2 in 11, we could answer this as y raised to the 5. And then of course, we have one more y left over, so that can be left in the house. So if you want to do it in a more mental kind of way, you could do it this way. If you want to look at more of your exponential rules and sort of leverage that, you can look at it this way. And if you want to literally say, hey, I got 11 y's here multiplied times each other, and I'm going to put them in groups of 2, and if for every group of 2 I see of y's in the house, I put one out the house and do it this way, then that's fine. Either way is fine. All these ways you still end up getting the same answer. Okay, just trying to give you options on what would work best for you. All right, so let's move on to number 8. All right, so for number 8, it's more of the same, but now we actually know what the number is under the radical. And of course, it's 81. Okay. Now, if we're looking here, we know that this 3 is telling us, or the index 3 is telling us, we need to have like factors multiplied together at least 3 times to be able to take one of those factors out the house. And so we'll start off here by just trying to figure out, well, 81 is what times what? Well, we know that 81 is just 9 times 9, right? So simple enough. But here we know that 9 is not a perfect cube. So since we know that, we can break this down some more. And we can say, okay, well, we know that 9 is just 3 times 3. And the other 9 is also 3 times 3. And in looking at this, we see that we have 1, 2, 3 3's that are being multiplied times each other. So for every group of 3 that you have in the house, you get to take 1 3 out the house. Okay. So all these 3's here in the house are equivalent to 1 3 out the house. And so now you see that you have one other 3 left inside of the cube root. And so here you just leave it in there like that. And this is the most simplified way to express the cube root of 81. Okay. Now for number 9, same sort of thing. We want to figure out the 5th root of 1,215. Well, you may not know what times what is 1,215, but one thing that I know that you know is that any number that ends in a 5 is divisible by what? Yep, that's right, 5. So we can start there. So we know that if I take 5 and divide it by, if I take 1,215 and divide it by 5, I know that 5 goes into 12 2 times, and that would be with a 2 remainder. 5 goes into 21 4 times, and that would be with the 1 remainder. And then I bring down the 5. 5 goes into 15 3 times. Okay. So right now I know that 1,215 is just 5 times 243. Now again, there's not much you can do with the 5, but the 243, we can break that down some more. And 243 is divisible by 3. And we know that because any number where if you add up all of the digits, and if that number is divisible by 3, then the number that you're trying to break down is also divisible by 3. So 2 plus 4 is 6. 6 plus 3 is 9. So that, and 9 is divisible by 3. So that means 243 is divisible by 3. So 3 does not go into 2, but 3 goes into 24 8 times, with no remainder, and 3 goes into 3 one time with no remainder. So here what we have now is a 243 is 3 times 81. Okay. Now, using what we know from the previous problem, we know that 81 is just 3 multiplied times itself 4 times. So we got this 5 times this 3, and of course 81 is just 3 times 3 times 3 times 3. So we got 4 more other 3's we need to multiply inside the house. And just like we talked about last time, we know that here this 5 means for every factor that is multiplied times itself 5 times inside the house, that would be equivalent to 1 outside of the house. So if you notice here, you got these 5 3's that are being multiplied by each other inside the house. So that's equivalent to 1 outside the house. And then, of course, you just have this 5 that's stuck inside of the 5th root, or stuck inside the house, and didn't have another 4 to pair up with, so it has to stay in. And so this would be your answer for number 9. All right, so let's move on to number 10 now. Okay, so for question number 10, this involves solving what we call rational equations. And so just like with regular equations, we want to figure out what values of x will make both sides of our equation equal. Now, to do this with rational equations, we want to take a different approach because in an indirect way, the equation is telling us what can't be a solution to it. And we also want to get this out of this rational equation form. And we want to get into a form that we're a little bit more familiar with dealing with, okay? But we do have some pre-work that we need to do first. So first thing that we want to do is, of course, rewrite this equation to where our denominators are factored out completely. And of course, here on the right side of our equation, we need to factor out our denominator here. And this just end up being x plus 4 times x plus 3. Now, in seeing this, we know that if we were to plug in a value of -4 here, that would give us 0 in the denominator. And if we plug in the value of -3 here, that would give us 0 in the denominator. And we know that we cannot divide anything by 0 because anything divided by 0 is undefined. Okay? So in looking at this, what this tells us before we get started is that x equals to -4 or x equaling to -3 cannot be a solution to this equation. We know that getting started. Okay? So the reason why we need to point this out is because if we have an equation and we solve this equation and it ends up being that one or more of our answers are going to be -4 or -3, we have to throw that answer out. Okay? We call that an extraneous solution. Okay? And I'll spell the word for you. Extraneous solution. I like to say it's extraneous to try to help me to remember how to spell it. But it's an extraneous solution. That's a fancy way of saying, hey, you have a solution that the process that we're going to do will give you as an answer, but it's not truly an answer. Okay? And in this specific case, whenever we get solutions that are extraneous, what that actually means for these types of equations is that the only place where the graph of the function that is on the left of this equation and the function that's on the right of this equation, the only places where they intersect is places that have a discontinuity. Okay? And with rational functions, we have this thing called vertical asymptotes. Okay? And we don't cover it in this class per se, but what it is basically a discontinuity in the graph of a function where As that function gets closer to it, it either tries to climb above it or dig below it. It's kind of like a wall that's there, okay? And the function is just basically undefined there. And so whenever we have these extraneous solutions, all it's saying is that the only thing that it has in common is these places where on the graph of both of those functions where it's undefined, okay? And we just throw those out. Now, this is the first thing we need to pay attention to. We start off by trying to find what the solutions can't be before we actually figure out what the solutions are, okay? The next thing that we want to do is find out what is our LCD, okay? And for our three fractions, quote unquote, in this particular equation, our LCD will be x plus 4 times x plus 3, okay? And so now, one way that you can do this problem, knowing that you know this information, one way that you can do it is you can just form equivalent fractions with the left side of this, since the right side already has everything that it needs, okay? So if you notice here that we got the 1 over x plus 4, what it's missing in the denominator is x plus 3. So you can multiply numerator and denominator by x plus 3. Same thing, second term, this one is missing the x plus 4. So you multiply numerator and denominator by x plus 4. And I'm going to put parenthesis around this just to make sure that you know that for the 2 here, you're going to multiply it by both terms. And we'll write this as normal. All right, so from here, if we multiply, we'll get x plus 3 plus, and then we multiply the 2 here, there'll be 2x plus 8. And all of that will be over x plus 4 times x plus 3. And then that'll be over negative 1, x plus 4 times x plus 3. Okay? Now, once that's done, then we'll combine like terms here. And we see that we'll get x and 2x is 3x. And 3 plus 8 is 11. X plus 4 over x plus 3 in the denominator. That'll be negative 1 over x plus 4 times x plus 3 in the denominator. Okay. Now notice that at this point in the problem, since the denominators are the same and equal, then that means that the numerators have to be the same and equal. So from here, we can deduce that 3x plus 11 has to equal negative 1, and we can solve for x. So in solving for x, we can subtract both sides by 11. Negative 1 minus 11 is a negative 12. We divide both sides by 3, and we end up getting x is equal to negative 4. Okay? So you see here that we have x equals negative 4 as our solution to this equation. However, do you notice that negative 4 was actually one of those extraneous solutions that we talked about earlier? And so whenever we see this, we know that we have to throw out that solution. And so since we don't have anything left, we know that the answer to this question is actually just no solution. And you can either just write no solution or put the circle with a line through it. And again, what this means is that this equation is asking you, hey, you got two functions. The function that's made up from the left-hand side expressions being added together and the right-hand side expression. And you're trying to figure out where those two functions intersect each other on a graph. And the only place that they have in common on a graph is a place where they have a discontinuity, which is at x equals negative 4. Okay, so that's one way to do this problem. I'm going to erase what I have here and then approach this problem another way by using an LCD to get rid of the fractions. And so this is another alternative way you could do this problem. Now, another way that we could do this same problem here is to take this equation that we have here, and let me erase this business, but to take this equation and multiply both sides of the equation by the LCD, okay? And if we did that, that would look something like this. So I'll just come down here to do it. So we would say x plus 4 times x plus 3, and all that will be multiplied by 1 over x plus 4 plus 2 times x plus 3. Then here, this will be negative 1 over x plus 4 divided by x plus 3. And all that will be multiplied by x plus 4 times x plus 3. Okay. Now, in doing this, when we multiply the x plus 4 times x plus 3 to both terms, what this will literally come out to be is this. For the first term, you just have x plus 4 times x plus 3 over x plus 3. The second term, you will have 2 times x plus 4 times x plus 3 all over x plus 3. And then on the right side, you will have a negative x plus 4 times x plus 3 over x plus 4 times x plus 3. And starting from the left here, you see how we had the x plus 4s here. They will reduce to 1 and just leave us with x plus 3. Here, the x plus 3s reduce to 1, and this just leaves us with 2 times x plus 4. And if we went ahead and multiplied the 2 to both terms there, that would be 2x plus 8. And then on the right side of the equation, the x plus 4s reduce to 1, and the x plus 3s reduce to 1. And we have a negative times positive 1 on all these sides, that just gives us positive 1. Continuing on, we see that x plus 2x is 3x, and 3 plus 8 is 11. Let's make that an 11. All right, so let's get that going. We'll make that an 11. That'll be minus 1. And so now we are right back to where we were before the first time, where we have 3x plus 11 equals negative 1. And here we would just solve for x. And we see that we would still end up getting x equals negative 4. But since that's an extraneous solution, we can't use that. And so our answer is just no solution. So you see, either way you go about doing it, you still get to the same result. Okay. And so the reason why I introduced the second way is because it's similar to the way that we did problems in weeks 1 and 2 whenever we were solving linear equations by multiplying both sides of that equation by the LCD. Okay, so you can do it either the first way or the second way. Doesn't really matter. Whichever one makes the most sense to you, that's the one that you want to do. All right, let's move on to the next problem. All right, so this is another rational equation. And so just like how we did before, the first two things that we want to do is figure out what are going to be our values of x that we know that we can't have as a solution. And we also want to know what the LCD is, so that we can either form equivalent fractions, and once we have the denominators being equal, we can make the numerators equal, or we can use the LCD to multiply both sides by the LCD of the equation to get rid of all of our fractions. So first things first. So here we need to factor out the denominators as much as we can, and if we do that, we'll get 2 times x plus 1 on the left side, and on the right side for our first expression we'll have 4 times x plus 1 plus 2x minus 3 all over x plus 1. So the one thing that we see here for all of our denominators is that if we were to plug in a negative 1 in for x here, negative 1 plus 1 would be 0. So we know that x cannot be equal to -1. That's the first thing that we know. The second thing that we know is that if we looked at 2 times x plus 1, 4 times x plus 1, and x plus 1, that the least common denominator amongst these three denominators will just be 4 times x plus 1. Okay? And so using that, this time I'm going to actually use multiplying both sides by the LCD first. Do it that way, and then I'll come back and do it the way where we just make equivalent fractions. So if I multiply both sides of my equation by 4 times x plus 1, then when I set it up, this is what it's going to look like. So I'll just do 4 times x plus 1 here, minus 2x over 4 times x plus 1, and plus 2x minus 3 all over x plus 1. Okay. Now, of course, here, since we only have one term, this makes this simple to do. The x plus 1s here will reduce to 1, and 4 divided by 2 is just going to be 2. So on the left side here, we just have 2 times 1 times x, which is 2x over 1, which is just 2x. On the left-hand side here, we multiply both terms by the 4x plus 1. Then whenever I do this, this will end up being a negative 8x times x plus 1 over 4 times x plus 1, plus this would be 4 times x plus 1 times 2x minus 3 all over x plus 1. And here we know that these x plus 1s would reduce to 1. 8 divided by 4 is just 2. And these x plus 1s here would reduce to 1. So what we would end up with is 2x on this side, and we would have a minus 2x for the first term here. And then this would be plus 4 times both of these terms here. So that'll be 8x minus 12. And once you see that, we essentially have a linear equation, and we can solve for x now. So we keep on going here. We know that negative 2x plus 8x is positive 6x plus 12. Come here. We could subtract 6x from both sides. And if we did that, that would give us a negative 4x on the left and a positive 12 on the right. Divide both sides by a negative 4, and we will get x is equal to negative 3. And if you see here, the only extraneous solution that we have is x equals negative 1. So this answer does not have to be thrown out. And assuming that all the math is right here, we will say that this would be the correct answer. But I see that I missed a sign here. Yeah, I just saw that. So this should be a minus 12 here. So I apologize for that. That should be minus, so which means this should be minus, and that should be plus. Yeah. So I guess I was looking at the positive here instead of the negative there. So this ends up being a positive 3, and this would be our final answer here. Okay. All right, let's move on to number 12. Okay, so the purpose for number 12 is to give you situations where you are dealing with a rational expression, but that rational expression is all, all variables, okay? In particular, this equation sort of mimics the gas laws that you will see in either a physics class or a chemistry class. And the P's stand for pressure, the V's stand for volume, and the T's stand for temperature. Okay. And so what you're trying to do is, if you are trying to go from one state to another, you're trying to figure out the pressure of the second state, or the pressure of the second device, or whatever it may mean in, let's say, a chemistry or a physics course. Now, mathematically, we're not really too concerned about that. All that we're concerned about is we want to solve for this particular variable. And so that means we want to get this variable by itself. Okay. Now, the simplest way to do that, here, if we want P sub 2 by itself, is we need to get rid of V2 and T2 on the right side. Okay. And if we wanted to do that, I'm just going to rewrite this. The easiest way to do it is to multiply both sides of this equation by the reciprocal of the fraction V2T2. And of course, the reciprocal of V2T2 is just T2V2. So we would multiply both sides of the equation by T2V2. And what that does on the right-hand side, when we do that, and I'll finish writing it over here, is that will reduce the T2s to 1 and the V2s to 1, and we just have P2 by itself. Now, the price that we have to pay for that is we got to multiply all this together. But of course, the beauty in this is that since we do not know when any of these variables are number-wise, all we have to do is just write it together like this. And so literally that is just the answer. All right, so now let's look at questions number 13 and 14. Questions number 13 and 14 are about dealing with radical expressions and simplifying them. And of course, this is different than what we've done with rational expressions or rational equations, like the last few problems that we've been working on. So I want to demonstrate how we do this. So to get started, the first thing that we see here is that we have square root of some expression divided by square root of another. Okay, and so one of the things that we know we can do is anytime we take the square root of something divided by the square root of something else, we can put that all under one big square root. So that'll be square root of 189 x to the 5th, y to the 6th, divided by 3 y to the 4th. Okay. Now, from here, remember that square root of whatever is under here just means that we have all this raised to the 1/2 power. That's another way of thinking about it. My point in saying that is that we want to work on everything inside of the square root first before we actually do the square root part of it. Okay, so what I'm going to do here is I'm just going to write this as 189 divided by 3 times x raised to the 5 divided by 1 times y to the 6 divided by y to the 4. Okay, and I've done this to separate everything to where now you can see what's under the radical in terms of everything that's just dealing with numbers, x's, and y's. Okay. Now, with that being said, we know that 189 divided by 3, that's going to end up being 63. And x raised to the 5 divided by 1 is just x raised to the 5. And y raised to the 6 divided by y raised to the 4 is the same as saying y raised to the 6 minus 4, which is just y raised to the 2. Okay? 6y's above, 4y's below. Once we have the 4 y's in top and bottom reduced to 1, we have a net 2 y's in the numerator. So now, from here, we can now take this and split this up as square root of 63 times square root of x to the 5th times square root of y squared. Okay. Now, square root of 63, we know that 63 is just 9 times 7. So we could break up square root of 63 as just square root of 9 times square root of 7. x to the fifth, we know that square root means how many, square root just basically means what do you have to multiply times itself twice to get x to the fifth. But since we don't know what x is, a way that we can think about it is how many groups of 2 are in 5, and we know that that's 2. So we could look at this in this way of we have x to the 5, and I'll just list this out all the way and then erase it to make sure it's clear to everyone. So here we have 1, 2 groups of 2 for the x's, and so for every 2 x's that we have in the house, we have 1 that's out the house. So here we got 2 groups of 2, which gives us x squared here, and then we have this last x that's stuck inside of the square root, so we would have to rewrite it that way. Okay. And then of course square root of y squared, we learned back from question number 2 that initially we would want to answer this as absolute value of y. Okay. But since all of my variables represent positive real numbers, meaning that y here is considered to be greater than 0, and so is x considered to be greater than 0, I can simplify this absolute value of y to just y. Okay? And so now once we're done here, square root of 9 is 3. Can't break down 7 anymore, so I have to stay under the radical. And we know that absolute value of y will just be y in this case because y is considered to be greater than 0. So we'll erase all this. And didn't mean to erase that though. So we'll go ahead and put that back. And so now everything that is outside of the house, so to speak, the 3 and the x squared and the y, we multiply that together. 3x squared y. And everything that is inside the house, which is the 7 and the x, will remain inside the house. And so this is our final answer for this question. So 3x squared y, all that times square root of 7x. Now, when we do number 14, it's going to be very similar, but what's different in this case is that we're now dealing with cube root. We have to switch our thinking to dealing with cube root, meaning we got to have factors of 3 of the same thing being multiplied times itself under the radical to pull one out versus just having 2. But other than that, everything else is the same. So we start off here writing as one big cube root, 32, a to the 4, b to the 6, divided by 4a. And so just like how we did last time in question number 13, what we want to do is simplify as much as we can here on the inside before we actually take the cube root. So you see I'm just rewriting everything in terms of numbers and the associated letters. We know that 32 divided by 4 is 8. A raised to the 4 divided by a, it's the same as a raised to the 4 divided by a raised to the 1, which would be in that 8 raised to the 3. And then of course b to the 6 divided by 1 is just b to the 6. So from here, we'll split this up. We've got cube root of 8 times cube root of a cubed times cube root of b to the 6. Now, we know that if we multiply 2 times itself 3 times, we'll get 8. So we know that the cube root of 8 is 2. We know that the cube root of a cubed is just going to be a, because we could rewrite this as a raised to the 3 divided by 3. And of course, once we simplify all that, that would just end up being a. And since the index is odd, and because of the fact that A is considered to be all positive real numbers, we know that we won't have to do the absolute value of A thing, like how we have to do with the even and groups. Okay, and we also know here that the cube root of b raised to the 6 can be rewritten as b raised to the 6 divided by 3. Of course, if we simplify what we have going on here, we got 2a raised to the 1, b raised to the 2, which will just simplify to 2ab squared, because a raised to the 1 is just a, and of course 6 divided by 3 is 2. And this is your final answer. All right, so let's look at number 15. So number 15 has the same instructions as number 14 and 13. What's different here is instead of us having to do all the division first, we just have multiplication. So if we come here, we can split this up and do the 5th root of 32 times 5th root of x raised to the 4 times 5th root of x raised to the 17. Okay. Now, the 5th root of 32 is just 2, because if you multiply 2 times itself 5 times, you'll get 32. Okay. If you don't know that right off the bat, that's fine. One of the things that you do know is that 32 is divisible by 2. Okay, and of course, 32 divided by 2 is 16. And if you take 16 divided by 2, that's 8. And if you take 8 and divide it by 2, you'll get 4. And if you take 4 divided by 2, you'll get 2. So you got 1, 2 here. So once you get through doing all that, you'll see that 32 just breaks down. And I'll just keep writing it this way. 4 times 4, 2 times 2. So 32 is just 2 multiplied times itself 5 times. So we know that because of that, 5th root of 32 is 2. For this next factor, the 5th root of x to the 4 is just going to remain 5th root of x to the 4, because x to the 4 means x multiplied times itself 4 times. And we need at least 5 x's being multiplied under the radical of the 5th root for us to be able to pull 1 x out. So there's not much we can do with that. Okay. But for the next factor, we see that we have the 5th root of x raised to the 17. And of course, if we look at 17, we know that 17 has 3 groups of 5 in it. Okay. So because of that, we would have x cubed out as a result for that, because the first group of 5 would have one of the x's, second group of 5 would have the second x, third group of 5 would have third x. And then of course, what's trapped after we take the first 15 x's into account, or the 3 groups of 5, we have 2 x's that are left under the radical. And that's how we have the x squared under the radical. And so, and that's, sorry, that should be y, not x. So let me change that. So that should be a y there. And that should be a y here. So I apologize about that. So everything I was saying here about the x's really should have been y's, because I forgot to write that. All right, so once that's done, then everything that's outside the house, we multiply together, and everything that is inside the house, we multiply together. And so you see that we just have 2x cubed times the 5th root of x to the 4th y squared. And this is your final answer for that. All right, so I'm going to erase this work here, and we'll talk about numbers 16, 17, and 18. Now, the purpose of questions 16, 17, and 18 is to get you to really understand and respect that anytime we take some fractional exponent form of something and we want to rewrite it in radical form, this is the conversion that we make, okay? This is the equivalent form of saying that. So in looking at this, when we look at number 16, we have to remember that order of operation says that we have to do exponents before multiplication. So we're literally looking at this problem this way, okay? Which means that this will be 3 times the 7th root of x cubed if we take this part here and convert it according to what this particular rule says about taking variables raised to a fractional exponent and rewriting it in radical form. Okay, so that would be the answer to number 16. For number 17, if you notice the 6x is inside the parentheses, so whatever this placeholder x is here, it will now be replaced with 6x. So literally you have the 5th root of 6x, all that raised to the power of 3. Okay? And so here, you know that if I was to rewrite this, this would be 6 raised to the 3 times x cubed, and 6 raised to the 3 would just be 216 x cubed here, okay? And so here we know at this point, because we have 3 6's multiplied times each other and 3 3's multiplied times each other, we're not going to be able to simplify this anymore, okay? So prefer you to leave the answer this way, but there's not anything technically wrong with leaving it that way, okay? I just want everything to be simplified, so that's why these instructions here say simplify, and we want the 216 below that. All right, so for number 18, when we do this problem, we can rewrite it as the cube root, because here we know the 3 here, same as goes with the index, and the 1 there, it's in the place of m, will go here. So it's going to be the cube root of negative 512 x raised to the 15 and all that raised to the 1, which is simply just cube root of negative 512 x raised to the 15. Okay, and so here we can do some reducing here. So one of the things that we want to take into account of is that we want to look at the cube root of negative 512 times cube root of x raised to the 15. And I'm going to go ahead and move this up some so we have some more room. So now from here, we have to figure out, well, all right, well, what's going to be the cube root of negative 512? Okay. If you don't know that right off the bat, again, that's fine. But what you do know is that 512 is a number that is divisible by 2. So we take 512 divided by 2. We know 2 goes into 51. 2 goes into 5 2 times with a 1 remainder. 2 goes into 11 5 times with a 1 remainder, and 2 goes into 12 6 times. Okay. May not know what 256 is as far as what it's broken down into, but it's also divisible by 2. 2 goes into 2 once. 2 goes into 5 2 times with a 1 remainder. 2 goes into 16 8 times. And for 128, may not know that, but you know it's also divisible by 2. And so 2 goes into 12 6 times. 2 goes into 8 4 times. And of course, now we're starting to get more clear, because we know that 8 is just going to be, 64 is just going to be 8 times 8. So my point here is, if you didn't know what 512 multiplies out to be, What you do know right now is this, is that it's going to be a negative 2 times 2 times 2, and then we know 64 is just 8 times 8, and the 8's here are just, yeah, that's kind of out of place here, so let me correct that right quick. All right, so as I was saying before, the 8's here are just 2 times 2 times 2, so 2 times 2 times 2. So the 64 here is just 6 2's, 1, 2, 3, 4, 5, 6. So we got that. So this is how we could break up that cube root of negative 512. And we know that the cube root of x raised to the 15, according to what we see here, can be rewritten this way. Now, we know here that we need to have groups of 3 of these 2's here. So you got one group of 3, 2 groups of 3, 3 groups of 3. And of course that negative I'm leaving there. I'm actually going to rewrite this here as an understood -1 right here. So I'm going to try to do it like this and then just move it in there. It's going to be like an understood -1 that's going to be on the inside of that. So for every group of 3 we have in the house, we have 1 outside of the house. And the cube root of -1 that's left would actually be -1 as well. And then, of course, the x raised to the 15 divided by 3 is just x raised to the 5. Okay. And so again, with this -1 that you see here, we know that cube root of -1 is just -1, because -1 times itself 3 times is -1. So we got all that here to say that we got -1 times 2 times 2 times 2, which is -8. And then that'll be x raised to the, what is that? This should be 5 here, because 15 divided by 3 is 5. And so this is your final answer for number 18. All right, so moving on to question number 19. 19 says we want to multiply the expressions together and simplify as possible. And we want to assume that all variables in this problem and other ones like it are positive real numbers. And so again, all that means is we have something like square root of x squared or the 4th root of x to the 4th, that we can answer this as just x and not have to do the whole absolute value thing. Okay. All right. So in this case, if you notice, everything's the same except for these signs here. And so what that means is that these two are conjugates of one another. So this looks like a minus b times a plus b. And we know from earlier in this course that a minus b times a plus b is just a squared minus b squared. So for this problem, if we note that a is square root of 10, and that b is square root of 6, literally we could look at this and say this is square root of 10 squared minus square root of 6 squared. And anytime we take the square root of something and square it, that just undoes the square root sign. So we're literally just looking at it as 10 minus 6, and of course that equals to 4. Okay. Now, that's one way to do it. This is the shortcut way to do it. If you don't understand this way or you think you're going to get it wrong, then what I would suggest you to do is the FOIL method way, which is the traditional way of doing this problem. I'm going to go ahead and do that right now. So, doing it the FOIL method way, we would say here, do first, which is square root of 10 times square root of 10, we know that here, anytime we multiply two numbers and both of them have the same index, which is the 2 here, we can put it all under the same radical. So 10 times 10 is 100. Then we do the outside, and that would be minus square root of 60 inside plus square root of 60. And then last would be minus square root of 36. And if you notice, these two terms on the inside cancel to 0. We know that square root of 100 is 10. We know square root of 36 is 6. And you see that we get 4 as our answer that way as well. And so it's because we know that these two middle terms here will cancel. Whenever everything is the same in both of the terms that you're multiplying except for the sign, we say that in those cases, those two expressions are conjugates of each other. We can use this formula here to get the answer quickly. Okay, but again, if you don't feel comfortable with that formula, you can always just multiply everything via the FOIL method, and you'll still get the same answer. All right, let's move on to number 20. So number 20, same kind of thing. Here we can use shortcut method, or we can do the long way. I'm going to do the long way this time, and then afterwards do the shortcut method. So long way, I'm going to multiply 9 times 9 is 81. Then do the outer, and that'll be a minus 9 times cube root of 3. Do the inside, that'll be plus 9 times cube root of 3. And then the last would be here, which would just be, not plus, be minus, because I got a positive times a negative is a negative. And this will be cube root of 3 times 3, which would just be cube root of 9. And so here the two middle terms cancel again. And you just have 81 minus cube root of 9. Okay. Now, if you did this the shortcut way, this is what this would look like. Let me go and erase this right quick. I don't want to do all that. Just erase this part. So if we do this the shortcut way, we know that this looks like a plus b times a minus b, which we know that this will end up being a squared minus b squared. So if we look at it this way, then of course this problem will end up being 9 squared, because a would be representative of the 9 and b would be cube root of 3. So we'll have 9 squared, and then we'll have cube root of 3 squared. And of course 9 squared is 81, and cube root of 3 is like saying cube root of 3 times cube root of 3. And of course, since you have the same index here, we can multiply what's under the radicals together. You'll have cube root of 9. And so you still get the same answer. All right, so for number 21, if you notice, these two expressions are not the same everywhere except for these signs. So you would have to do the FOIL method for this, and there is no other way to do it. Okay. So in doing the FOIL method here, just multiply. We'll have square root of 11x times square root of 11x. That would be square root of 121x squared. And note that anytime we multiply the square root of something by itself, it actually just ends up being the number under the radical. Okay. And to kind of go back and make sure that you understand that, going to go back to question number 19 to show you that. So if you remember, let me go back here. You remember how for question number 19, whenever we said square root of 10 squared, what that really was is us saying square root of 10 times square root of 10. Okay? So anytime we take the square root of something and multiply it times itself, we get what's under the wrap. You see how we said square root of 10 quantity squared, which is the same as this, ended up with 10. Okay? The same thing with the 6. So my point here is that on this problem, anytime we see square root of whatever being multiplied times itself, we can just write what's under the wrap. So the first part of the FOIL method is just going to be 11x. The outer part will just be -3 times square root of, and in this case, since square root of 3 and square root of 11x aren't the same, but they have the same index, we can multiply the 11x and the 3, and we'll get 33x under the wrap. When we multiply the inside, we have a -3 again, and since 7 and 11x are both under the square root sign, we can multiply that together, and that will give us -77x. And then the last here, the negative times a negative gives us a positive. 3 times 3 gives us a 9. And square root of 7 times square root of 3 would just give us square root of 21. And surprisingly, this is our final answer. This is about the best that we can do with that. For some of you, if you want to get fancier, you don't have to. You could factor out the -3 and just do let's say square root of 33x minus 77x. You could do that if you wanted to, but you don't have to. Okay. Some of you can get even fancier and factor out the common square root of 11x out of everything, but again, it's not going to really help you any because you don't know what x is. So I would suggest that you refrain from doing all of this and you just stick with this answer. Okay. All right, let's move on to question number 22. All right, so for question number 22, this problem basically says that we want to take this expression here and multiply it times itself twice. So literally, we're taking 3x minus 4 under this square root, all that minus 5, and we want to multiply it times itself twice. Okay? And so once we're here, we'll do the FOIL method just like we have been doing. So anytime we multiply square root of anything by itself, we know it's just going to be whatever's under the wrap. We do the outside part, that'll give us a -5 times square root of 3x minus 4. Inside part gives us another -5 times square root of 3x minus 4. And then the last part, negative times negative is positive. 5 times 5 is 25. So now all we need to do is simplify. So the first thing that we see here is that these two middle terms will combine to be a -10 times square root of 3x minus 4 plus 25. And then we notice that -4 and 25 are like terms. So -4 plus 25 gives us a positive 21. So we'll write out all these other terms. And I have a plus 21 there at the end. And that will be our final answer for number 22. All right, so for questions number 23 and 24, we're asked to either add or subtract these radical expressions together. And of course, for both of these problems, what we have to do to start off with is to try to simplify each term as much as we can so that we can we can determine whether these terms are indeed like terms or not. If they are like terms, we'll combine them together. If they're not like terms, then we'll just write the answer however it is once we're done. So first thing that we want to do here is for the cube root here, just going to break up everything, do cube root of x cubed times cube root of y raised to the 13, and then 3xy times cube root of 27 times cube root of y raised to the 10. I'm going to deal with that separately. Now, the cube root of x cubed, as we mentioned way back in question number 2, we know that that's just like saying x raised to the 3 divided by 3, which is x raised to the 1, which is just x. So the cube root is undoing the cube on the x here. So that is just x. And since the index is odd, and because all of our variables represent positive real numbers, we don't have to worry about the absolute value thing. Now, for cube root of y raised to the 13, we know that here y raised to the 13 is just 13 y's being multiplied times each other. And this 3 in the index is telling us for every group of 3 y's that we have, we can pull one out. Since we know that there are 4 groups of 3 in 13, that means that we have a total of 4 y's that are going to be pulled out, because 4 times 3 is 12. We have 1 y that's remaining, that's stuck in the house, that doesn't have another 2 to pair up with to also come out the house, so it has to stay in the house here. Okay, so then we'll write down the 3xy. We know that cube root of 27 is just 3, because 3 times 3 times 3 is 27. And of course here, just like with the y raised to the 13, we look at this and we say that, hey, we know that 10 has 3 groups of 3, so that's going to give us 3 y's that we can take out, and 3 times 3 is 9, so that leaves us 1 y left over inside the house. Okay. Now, when we start to multiply all this together here, we'll get 6xy raised to the 4 times cube root of y. And here we have 3 times 3, which is 9x, and then y, which is the same as y raised to the 1, times y raised to the 3 is y raised to the 4, times cube root of y. And here, do you notice how both this term and this term all have the x times y to the 4th times cube root of y in it? Okay, and so what that lets us know is that these two terms are indeed like terms. The only thing that's different about it is the coefficients. So here, when we do 6 minus 9, that gives us a -3, and everything else is the same. Okay, and so if you don't like the way that I did that, then another way that we can think about it is like this. We have 6 minus 9, and we'll pull out the greatest common factor of x, y raised to the 4th times cube root of y here. And we know that 6 minus 9 is a -3. That's another way of looking at it. So either way, this ends up being your final answer for number 23. And so number 24 will be similar. We'll break down each term as much as we can and then try to add what we can. All right, so for here, we see that we have square root of 3 and a. Since we can't break down 3 anymore, and we can't break down a anymore, we'll just leave this as square root of 3a. Plus 3, and now let's try to see if we can break down square root of 108a. Now, what we do know is that 108 is the same as 12 times 9, or as I'm going to write it, 9 times 12. So we could say this is square root of 9 times square root of 12 times square root of 8 plus 5 times 75. We know that that's just 25 times 3. So 75 square root of 25 times square root of 3 times square root of 8. So if we keep going here, we'll see that square root of 9 is just 3. Square root of 12 can be broken down to square root of 4 times square root of 3. And then we still have that extra square root of a that's there. We know that square root of 25 here can be broken down to just 5, because square root of 25 is 5. And then we got square root of 3 times square root of 8. If we keep going, we see that 3 times 3 is 9. Square root of 4 is 2. We got square root of 3 times square root of a. And 5 times 5 is 25 times square root of 3 times square root of a. All right, so now we have square root of 3a plus 9 times 2 is 18. And here, since the 3 and the a do not have anything else to pair up with to get more out the house, we just multiply it and keep it in the house. And same thing here with the last term. The 3 and the a's here don't have much left paired up with, so we keep it all in the house. Okay. And so now when we look at this, we know that this term, this second term here, is 18 times square root of a plus 25 times square root of a. And here we just have a square root of 3a. And here we have an understood 1 that's here. Okay. So we want to make sure that we recognize that. So now when we look at this, this is like saying 1 apple plus 18 apples plus 25 apples. Okay. So when we look at this, if we combine like terms, when we look at this, this will just literally be 44 square root of 3a. Okay. Now, if you don't like the way that I just kind of looked at it and did it, notice that here, square root of 3a is a common factor amongst all those terms. So here I could rewrite this as 1 plus 18 plus 25, and then factor out the square root of 3a. And of course here 1 plus 18 is 19, 19 plus 25 is 44. And so you could get it that way too. So either way, you will still end up with the same answer. So this concludes the review for quiz 5. I know, again, it was a long video, but I wanted to make sure that I gave you plenty of examples of the types of problems that you'll see, regardless of what version of the test you get. Hopefully this is helpful. If you have any other questions, please let me know. Take care.